My name's Ron. I'm from Metronome. So to give you an idea, I always start just a little bit with who we are because some folks have our history in their mind and some folks don't know us at all. I see a couple folks in the audience that know us pretty well. So we're Metronome. We've been around for about 11 years now. We provide network connectivity solutions, so server networking solutions for telcos, cloud data centers, etc. It's the old class of SmartNIC. If you've heard that name, it's come back around again, and we believe we have the most effective solution in that environment. So what we're seeing now in this space is that as network connectivity increases in speed, now going from 10 to 40, or 10 to 25, and then to 100, more CPU resources are being allocated to process networking functions. And clearly this is an illustrative chart, but the concept here is that not only are we adding network connectivity functions or network functionality down on the endpoint servers as we're going to an SDN world and everything is becoming soft, we're also adding things like virtual firewalling. We're adding things like encryption, decryption at the server itself. So all of these edge devices that Eugene talked about for this multi-core edge or edge computing world, you're providing a lot more smarts to the edge. And because you're doing that, you're consuming CPU resources. And by doing that, you're actually bottlenecking the performance of the VNF or multi-tenant environment. So what we've done is we take our network flow processor and we've benchmarked this against general purpose CPUs. And one of the challenges is as functionalities are driven towards the edge, as we spoke about, you're having to consume cores, consume cycles. But if you have a pipeline built architecture that's especially designed for networking and you can offload critical features to that network card, you can get a lot better performance. So, way back when it was about 18 million packets per second that we could offload compared to 1 to 2. You can look at the CPU world. Our good friends at Intel are going to say use the CPU for everything, make everything soft. But the problem is you just can't get the packet throughput that's going to be required, especially as VNFs become more and more dense. And that's one of the problems that we're looking to solve here is how do you get more VNFs on a server? If you can deploy with one VNF per server, you're basically still in the appliance mode, and we want to get away from that. So as you're moving forward, you can just see typical throughput improvements. I was on a panel not too long ago at a service provider conference, and we were talking about speeds, and I tend to think of things from a network guy's perspective. Speed is not just adding bigger pipes, it's getting data to the application. And a lot of the software mindset folks think, well, if I just get a bigger pipe, I can put more content onto the server, I can move bits a lot faster. While that's true, we've done some benchmarking with 25 gig solutions, and if you're using 25 gig without offload, sometimes the best you can actually get in terms of throughput is about 6 gigs of throughput on a 25 gig NIC. That's not a configuration issue. Most of us, when we brag about our NIC speed, it's literally a ping test. It's how many packets can you get through or how many packets can you drop. But if you're actually going up to the server is doing a cache lookup or potentially a memory hit lookup for like a match action table, you're going to start slowing down your network processing. So having an actual pipelined architecture is going to improve that significantly. And how do we do that? And I think we talk a lot about improved efficiencies, but let's talk a lot about just a little bit about the underlying infrastructure. So this is your basic server architecture. You've got your orchestration layer on top, as the gentleman before me spoke about. You've got your agents, you've got your VMs, you've got, if you're running OVS, you've got your match action tables, you've got your tunneling, so if you're NCAP, DCAP for VXLAN. All of that is running in your kernel. That's just standard. If you use something like a SmartNIC, what we do is we simply mirror all of that virtual switch information onto the NIC itself. It still exists in the kernel. It still runs on maybe a single core, but we can actually pipeline. So a packet comes in, we can match that to our existing information. We can then take that flow and then send it directly to a virtual machine, and the packet won't even go up to the CPU until it's actually being run in the VM. Whereas with a traditional NIC, and my little joke notwithstanding, talking to the previous guy, Eugene, with a traditional NIC, the packet comes in, it's transported up to the CPU from a networking point of view. The CPU then takes care of the match actions, the lookups, the tunnel NCAP, DCAP, then sends it back to the NIC in order for it to be SRIOV'd or using DPDK, some type of transport mechanism to the virtual machine. So you've got hops in there that are taking a lot of time and slowing you down. So if you can get rid of those hops and you can pipeline your architecture, you're going to get better network throughput. So this is something our friends at Ericsson, we did some work with them. Using their Cloud SDN solution, if they needed 168 million packets per second, they could put about 80 VNFs per rack. But what was happening is they were consuming about 16 cores of their available cores simply due to OVS, and they were getting, therefore, about 8 cores to run the application. Now, I'm fine with people spending money on infrastructure, but most people don't buy servers in order to do networking. They buy servers to run applications. And what this came out to be, to support 220 VNFs, they needed 2.8, I'll call it 3, full racks of servers. So if you do an offload situation and those 16 cores that are being dedicated to OVS can now be used for the applications, and you can maybe reduce that core usage down to 1, so you can pin OVS down to 1 core. And if you do that, so there's some questions early on at our booth where someone said, well, why do you still have to run OVS in the kernel? Because it still has to exist there if there's a first packet miss or something like that. But now you can reduce it to 1 core instead of pinning it to 6 or 7, or sometimes even more in this case. And what you get is, to support the same number of 220 VNFs, you can go down to 1 rack of servers. So you got a 3-to-1 consolidation with the same network throughput. So it's not about going from 10 gig to 25 gig to 100 gig, which most people think about in terms of networking. It's about making your network much more efficient. One of our other partners is Juniper, and we support their open contrail, so people that are doing virtual routing. And I like to put this picture up because if you look, one of the things that I didn't cover here is it's almost the same picture. You still have the Linux kernel, you still have your virtual machines. Obviously, you've got routing involved, but you're still pulling information from OpenStack. But if you notice, let me see if I can get this correct. So this is a virtual routing table on the Agilio CX. Now, if we go backwards, what we've got is a switching protocol on the Agilio CX. So you can take the same network adapter, and you can run a virtual router, or you can run a virtual switch. So what you got is, with SmartNICs, you have full programmability. We didn't have that before in the network interface card world. And the reason we didn't have it before is our goal was to create the smallest, fastest turnaround chips so we can add network functionality. Maybe a different speed, maybe more ports, maybe a Geneve protocol. But with something like a SmartNIC, what you wind up doing is you can actually add protocols to that NIC while it's installed. So you can have a NIC that's just running as a standard NIC. You can add a virtual switch to that with a software load, or you can make it a virtual router. So it's a fairly simple process. Ours takes about 2 commands to do so. But you can see that instead of having servers that are dedicated to OVS and servers that are dedicated to virtual router, you can have fungible compute environments, which was, I think, something we're all kind of looking for. And just to give you an idea how this fits into this whole Contrail architecture mindset, it is using MPLS over GRE or MPLS over UDP. So it is truly a routing protocol on a switch on the edge. And what kind of performance deltas do we get here as well? So when you run the protocol on a standard NIC, you're getting sub 5 million packets per second. When you run the protocol with a smart NIC and do pipelining and offload, at small packets, we actually saturate the line so we can get over 25 million packets per second. Now, I always say you can always fill a pipe pretty easily with jumbo frames, but if you're running 200 byte packets or 500 byte packets, how do you get the most performance out of your network? And you're going to have to do that by some type of offload capability. So I actually, mea culpa on this one. There's an architecture slide that I forgot. And one of the things I want to bring up here is there's some added functionality that you can do with the SmartNIC. And if you can imagine an environment today where you've got service chain VMs, so what you've got is a switch talking to a server, and on that server you've got multiple VNFs. So you're going from one VNF to another to another. Almost what we're looking at is a black box there. So packet comes in, comes from the switch, goes up to the server. It's then transported to the first VNF, back down to the NIC, transported to the next VNF. Once it comes out, then we see it again, but we don't have a way of monitoring what's going on inside that environment. And with something like a SmartNIC, you can actually do things like insert metadata into the VXLAN packet using the general protocol extension header. So this is something we're showing at our booth. Come on by and take a quick look at it. We're inserting essentially a timestamp, and by inserting a timestamp at every single ingress and egress point, you can actually then start measuring not only how long does it take to get a packet from into the server and out of the server, but across every single step through that virtual machine. So you can see if you've got a performance bottleneck, which VM is giving you a performance bottleneck. So to give you an idea, just something like a commercially available monitoring tool like a Splunk, we created an environment where two VMs are talking to each other, packet comes through, we timestamp at the switch, at the NIC, at each VM, back to the NIC, and then out to the server itself. And you could see most, as would be expected, very little latency due to either the switch or due to the NIC itself. Most of the time that packet's in there, and we're using essentially latency as an analogy for performance. Most of the time the packet's stuck inside the virtual machine being processed. But what you can't see in a normal basis is if there's a performance spike, normally what you would see is from switch back to switch, Splunk would be monitoring how long it takes for that packet to get back. And you could monitor that, but you wouldn't know where the biggest bottleneck is occurring. And if you notice when you're looking at something like this, you see the virtual machine 1 or 0, virtual machine 1. When there is a spike, it is literally dedicated to one single VM. So the problem that's occurring is it's not due to the NIC, it's not due to the switch, it's not due to any other problem, it's just literally one virtual machine is seeing some type of random spike. And the idea is the insight. You only get insight into your network when you have granularity. This enables you to use the granularity to feed it up to a commercially available monitoring tool, and you can get more insight about what's going on inside your network. There we go. Just leave you with a very quick one. Who are we? What do we do? Standard. We have 10 to 100 gig, up to 2 gigs of RAM. All this stuff is details. Check it out on our website. We'd love for you to come on by the booth. We'll show you the demo, talk to you a little bit about cards. And I appreciate your time. Any questions? Come on, DJ, ask me a question. Thank you, folks.